So at the end of class yesterday, I did that demo with the volleyball, okay, and I held it up 2 meters above the ground, okay, and I said, okay, we calculated how much energy it had at that point. I think it ended up being like 5.3 joules, okay? And in that form, when I was holding it 2 meters above the ground, it had mechanical energy because it had what kind of energy? Potential, right, it was above the ground and could fall, okay? And then I dropped it. And I asked you how much energy, how much mechanical energy would it have the instant before it hits the ground? Okay, how much did we say? It had 5.3 up here. How much was it going to have right before it hit the ground? 5.3. Would it have 5.3 any spot along its falling path? Yes. Okay, it would have 5.3 joules of mechanical energy anywhere along its path. All that's happening is that the potential is getting converted into kinetic, okay? But the total number stays the same all the way along. Everybody all right with that? We're, of course, assuming there's no air resistance or anything like that to take energy away. So, let's try this, okay? Copy this one down and let's see how we do with it. Okay? Has anyone been to Knott's Berry Farm in Anaheim, California? Yeah? Okay. They have a ride called Montezuma's Revenge. Okay, it looks like this. It's a roller coaster. Okay, you get on the roller coaster right here. Okay, at this point, you have a height of 0. Okay, then you get towed all the way up here. Okay, and then you just kind of hang there for a second or two. Okay, and up here, you are 20 meters above the ground. Okay. Let's say that the mass of the roller coaster car is 650 kilograms. Now, when they release the car, okay, the car just obviously falls back along the track, and then it goes through the loop backwards, goes up to here, okay, and then stops and falls back through the loop. It does that like twice, and then you can't do it anymore because obviously this exists in the real world, and if you go more than twice, you won't actually have enough energy to get to the top of that loop anymore, and that could end badly. Okay, so you kind of go through it, through it, through it, and then back to the start again. Okay? All right, so knowing that it reaches a height, or it starts at rest at a height of 20 meters, calculate for me how fast it would be going here when it falls back through. Okay? And we're going to use the same principle as the volleyball. That the initial mechanical energy of the roller coaster, that's up here, okay, equals the final mechanical energy of the roller coaster, down there. Okay? See if you can calculate for me how fast the roller coaster would be going down there at its lowest point. Okay, give you a few minutes. I think you can figure it out. We'll give you a couple minutes on it. In case you're having trouble getting this started, think about this. Okay? We learned yesterday that mechanical energy is an object's potential energy plus its kinetic energy. Okay, and we know how to calculate potential energy and kinetic energy because we have formulas for both. Okay, so that means the mechanical energy here and here are equal. Okay, if you can figure out what kind of energy the roller coaster has here and what kind of energy it has here, you can probably figure out how fast it's going. Okay, see if that helps anyone who is stuck, and I'll give you a couple more minutes. Okay, let's now look at this one. What kind of energy does the roller coaster have perched up there 20 meters above the ground? It's not moving, so it only has potential energy. Can we calculate how much? Okay, and when it's at the bottom there, okay, we're trying to find out how fast it's going, but it has a height of 0, so obviously it only has what kind there? Kinetic. Okay, so what we're saying is the initial mechanical energy and the final mechanical energy are equal. The energy it has here and the energy it has here are the same number, not the same kind. Okay, so in the initial, so whenever we calculate mechanical energy, we have our potential energy plus our kinetic energy, and then here we would have the same thing, but final. Okay, now we just established that at the beginning, it's not moving, so it doesn't have any kinetic energy initial. And similarly, here where the height is 0, it wouldn't have any potential energy. So that means that its potential energy up there and its kinetic energy down here are equal. Because the law of conservation of mechanical energy says energy can't be created and it can't be destroyed. It can be converted into other forms, but the number's going to stay the same. Okay? So I have a formula that calculates this. It's m times g times h. And I have a formula that calculates that. It's 1/2 mv squared. Do I have all the parts of that equation except for VF? Okay. Can I solve for VF then? All right. So if I do that, if I want to solve for VF, I'm going to divide both sides by half the mass. Okay. What's actually going to happen to the mass there? What's m divided by m? It'll actually cancel. You don't have to cancel it. You can put 650 in there for both spots. You'll get the same number. Okay? But I could cancel m right there if I want. That's going to leave me with VF equals, because I have to square root it, the square root of g times h initial over 1/2. Okay? That's saying that the initial energy and the final energy are equal and that the potential got converted into kinetic. Okay, so, sorry, I forgot to fire up my calculator, guys. Pretty sure it comes out to about 19.8 or something like that. Okay, so I'm going to take the square root of 9.81 times 20 meters, so that's g times hi, and then I'm going to divide that by 1/2. Okay. So they'll be going 19.8 meters per second when they get back down to that lowest point. Okay, did we have to use any new formulas for that? Different application. Okay, different application of those same formulas, but still the same formulas. Okay, in the end, the only thing we needed to understand to solve this problem was that the energy of that roller coaster is the same number anywhere on that track. Okay? It would be the same here, here, at the top of the loop, here, halfway up the next hill, all the way at the top of the next hill. It's the same amount of mechanical energy anywhere along that track. Okay? Because energy can't be created and it can't be destroyed. Everyone okay with that idea? Okay. If you don't have that example copied down in your notes, copy it down right now. Okay? You can write at the top of it, level 1 conservation of energy problem. Give you a minute to get that copy down if you don't have it. Okay. this one a try here. Write this one down. You can call this like conservation of energy problem number 2. Okay? You have a 1.5 kilogram rock dropped over the edge of a cliff, 30 meters above the surface of a lake. What's the speed of the rock just before it strikes the surface of the lake? You can refer to your method from question 1 to help you with this one. Okay? Because if we're dropping something, what's its initial velocity? Zero. Okay? So you're holding it in your hand, so it's not moving. All right? So very similar to the last one. Okay? Just give that one a try, and let's see how we do. Some of it's already there, so you can kind of cheat off of it a little bit. Actually, don't cheat off of it. I don't like how they did that. Okay, just use the question there. I like how they're writing it. All right, so we are dropping a 1.5 kilogram rock, so that means our initial speed velocity is 0. Okay, our final velocity we don't know. Okay, we're looking for it, but we do know that our final height is the surface of the lake. So the final height is 0 meters. Everybody okay with my contextually given givens? Okay. So here's what we know. We know that the law of conservation of energy says that the amount of mechanical energy the rock has the instant it is dropped is the same as the mechanical energy it has the instant it hits the lake. Okay? What we have to decide is, okay, from this expansion, potential energy initial plus kinetic energy initial, okay, equals potential energy final plus kinetic energy final, okay? I'm still saying the same thing, I've just expanded it out. Mechanical energy is potential plus kinetic, okay? I have to decide from there if any of those are 0. How many of those are 0? 2 of them, okay? Because it's dropped and our initial speed is 0, just like the last example, we have no initial kinetic energy. Because the end of this question is hitting the surface of the lake, which would have a height of 0 meters, I would also have no final potential energy. So just like the last question, the initial potential equals the final kinetic, or the initial mechanical equals the final mechanical. Okay? I have formulas for both of those. M times G times H initial will calculate my initial potential. 1/2 mv final squared will calculate my kinetic. Okay? So now what I've got to do is solve for VF. Same as I did in the last question. So if I want to get VF by itself, I'm going to divide both sides by 1/2 of m. Okay? I can cancel m at this point if I want to. Okay? I want to because I don't like entering extra numbers, but you don't have to. You could put the 1.5 in there and you'll get the same number. Okay? Then I need to square root that to get VF. So VF will be the square root of G times HI over 1/2. Okay? So that'll be the square root of 9.81 times 30 meters divided by 1/2. Okay? So okay, so it'll be going 24.3 meters per second. Now, just to prove to you that you don't have to cancel the masses, I'll do that calculation again, but I'll keep the masses in. So I'll have mghi over 1/2 of m. Okay, so that'll have then the 1.5 times 9.81 over 1/2 times 1.5. If I put that in the calculator, I'm going to get exactly the same number. Okay, so it's totally fine to cancel the mass because mathematically it does cancel. Okay, everybody with me on that? Okay. Oh, I had that there. Okay. All right, because we've done 2 like number 11, I want you to try number 12. Okay, so we have a 30-kilogram child on a trampoline, jumps vertically into the air, and their initial speed is 1.6 meters per second. Now, you have to imagine, this is one of those trampolines that has the hole dug underneath it. Okay, so the trampoline is at ground level. So what's their initial height? 0. Okay, so they have an initial height of 0, okay, an initial speed of 1.6 meters per second. We want to figure out how high they will go. When they're at their highest point, how fast will they be going? Zero. Okay, you throw something up in the air, when it's at its highest point, it stops for an instant before it starts to fall back down. A little piece of information we need, obviously, to be able to do that question. Okay, so our final speed. Okay, so our givens look like this. Initial height, 0 meters. Initial speed, 1.60 meters per second. Final speed, 0 meters per second. Final height, that's the question mark. That's what we're looking for. Okay, and we have the mass, but you don't need it. You can cancel it, but you can write it down if you want. So again, what we have to realize here is that the law of conservation of energy applies. The initial energy of the child, initial mechanical energy, equals the final mechanical energy of the child. Okay? Initially, mechanical energy is EP initial plus EK initial. And then at the end, EP final plus EK final. Okay, initially the child is on the trampoline with a height of 0. Do they have any initial potential energy? None. Okay, but they are moving, so they do have initial kinetic. Okay, at the end, when they're at their highest point, we already said, at that point, they're not moving. So they don't have any final kinetic energy, only potential, because now there's some unknown height above the trampoline. So that means our initial kinetic equals our final potential. So 1/2 mv initial squared equals m times g times h final. I'm just trying to find h final. What do I do with m and g? Divide them over the other side. Okay, m's will cancel, and I just have to go 1/2 times 1.6 squared divided by 9.81. 0.5 times 1.6 squared divided by 9.81. Okay, this is not a very adventurous child. 0.13 meters is about that far. Okay, but they weren't moving very fast either. 1.6 meters per second is not very fast. You're not going to get very high if you only jump at 1.6 meters per second. Okay, everybody with me there? Still basically the same method. Okay, we just solve for an h instead of a b this time. All right, now they are going to get a little bit more complex. They're not always going to be initial potential equals final kinetic. You're going to get questions where you've got initial kinetic and initial potential and final potential and final kinetic. It doesn't change much other than you have a few more things to move around algebraically. The principle is still the same. Okay, let's talk about this picture here. If I'm holding that apparatus so it can't move, does it have energy? It certainly does. Okay, it's got some, if it's not moving, potential energy. Okay, now when I let it go, what's going to happen to the 1 kilogram mass? I got 2 kilograms on one side, 1 kilogram on the other over a pulley. If I let it go, where's the 1 kilogram mass going? Up. Okay, and the 2 kilogram mass is going to drop. Okay, so in this system, is the energy still conserved? Like, when this falls, will all of its energy turn into kinetic energy for it? No, it won't. Some of it will turn into kinetic energy for the 1 kilogram mass. And the 1 kilogram mass is not just going to gain kinetic, it's also going to gain potential because it's going to go up. Okay? But that's energy that's going to be lost by this because is it going to fall at 9.81 meters per second squared being attached and having to pull this other mass? Okay? So the amount of energy that this block loses is the amount of energy this block will gain. And so the total energy of the whole system actually stays the same. It's still conserved. You're never going to have to do a question like that in Science 10. Okay? But it's important to understand that if I have two objects connected to each other, that's a system. We talked about that early in the unit. Okay? And that the law of conservation of energy still applies. Because sometimes it might look like one part of the system is actually losing energy. But it's only because some other part of the system is gaining it. Okay? The energy is still conserved. Okay, let's look at this problem here. Okay, so I've got a bow and arrow system here. Okay, I use 100 newtons of force to pull the bowstring back half a meter, and then I aim it straight up in the air. How much work have I done? How do we calculate work?
Force times distance.
Force times distance. Okay, so what's 100 times 0.5? 50. Okay, so I do 50 joules worth of work. What's the work done on the bow? Work equals force times distance, which equals 100 times 0.5, that is 50 joules. Okay, how much potential energy is now in the bow? It's not gravitational. I did 50 joules worth of work on the bow. How much energy does the bow have now? $50 joules. Okay? The law of conservation of energy still works with work energy theorem. Remember, work is a change in energy. So if I do work on the bow has to gain that much energy for energy to be conserved. So if I do 50 joules worth of work on the bow now has 50 joules worth of elastic potential energy. Okay? If I release it and the arrow shoots out, how much energy does the arrow have? 50 joules. Because what does the bow do to the arrow? It exerts a force over a distance. Exactly the same as what I did to it. Okay, 100 newtons over half a meter. All right, so it would transfer all of that energy to the arrow, and the arrow would now have 50 joules worth of kinetic energy. Okay, everybody okay with that idea? So the two things go hand in hand. If you do work on something, that something has to gain exactly that much energy. And when it transfers it to something else, it has to transfer all of it, according to the law of conservation of energy. Okay? All right. Okay, the other thing we got to talk about, pendulum. Ghetto physics. Okay, this is what happens when you cut money from education. You get this, ghetto physics. Okay, now, right now, assuming that I can't drop this, how much energy does it have? I mean, if it can't fall, let's assume like there's right underneath, it can't fall. 0. Okay. Does it have energy now? Okay, why? I lifted it up. What did I do? Right, I did work. I put energy into it. What kind of energy does it have right now? Potential. Okay, let's say that at this position it has 10 joules of potential energy. Okay, I let it go and it just starts to do this. How much energy does it have at the bottom of the swing? 10 joules. How much does it have here? 10 joules. Here? 10 joules. Everywhere? 10 joules. That's law of conservation of energy, right? Okay? Once energy is put into a system, that energy can't be created and it can't be destroyed. If this was a perfect pendulum, which it is absolutely not, okay, it would swing for ever, okay, because it would never lose any energy. Okay? Obviously that's impossible. They're always losing energy. I have to keep swinging this thing to keep it swinging. Okay? But if it was a perfect pendulum, there's no air resistance or friction between my fingers and the string, okay, it would swing forever, perfectly converting all of that potential I gave it into kinetic and back and forth, back and forth. Okay? Everybody all right with that idea? All right. Okay. I want you guys to copy this one down. We're going to do this one as our first kind of big law of conservation of energy example. Okay, so you can label this one level 3 conservation of energy principle. So we've got the sledder on the hill here. We know that their starting point is 30 meters above the bottom of the hill. Okay, so that would be their initial height. Okay, we also know that this person did not start from rest. I mean, you rarely do when you're sledding, right? You usually give yourself a push or take a run at it. Okay, so they're moving at 1.5 meters per second to start. So we have an initial speed and an initial height. A little while later, they are moving at 7.5 meters per second and are obviously further down the hill. The question wants to know how far from the bottom, or what is their final height, now that they're moving at 7.5 meters per second. Okay? Can we safely assume that their mechanical energy is the same at the top of the hill and at the second point? We have to assume that, right? We're not told otherwise, so we can make that assumption. Okay? So if we can do that, that's how we start this question. Okay? We can start this question with the initial mechanical energy equals the final mechanical energy. Okay? And all conservation of energy questions start just like this. Okay? Then I need to expand that out. How do I calculate mechanical energy? Well, I add together potential and kinetic. And I do the same thing on the other side. Okay. Are any of those forms of energy zero in this question? No. Okay, we're 30 meters above the ground initially, so we have initial potential. We're moving at 1.5 meters per second initially, so we have initial kinetic. Okay, and then here at the end, we're moving at 7.5, so we have kinetic, and they're asking us to calculate the height. We have to assume it's not zero. Okay, so we've got all of these as actual values that aren't zero. I can't cancel any of them off. Okay, now they want me to find final height, which would be part of that term. Agreed? Okay. Before I plug in any more letters or numbers, can I isolate EP final? Okay, what do I have to do with EK final then? Subtract it over to the other side. Okay, so that's what I'm going to do before I put in the formulas, because otherwise it starts to get a little messy. Okay, so initial potential plus initial kinetic minus the final kinetic equals the final potential. So all I did was subtract EKF from both sides. Okay, so now it's over here. Right, now I'm going to put in my formulas. I can't go any further until I do. Okay, so EP initial, that's going to be M times G times H initial. I'm adding that to the initial kinetic, so plus 1/2 mv initial squared. And then I'm subtracting the final kinetic, so minus 1/2 mv final squared. Okay? And I said that that equals the final potential, so that'll be m times g times h final. Okay, using any new formulas yet? Okay, I need to get H final by itself. Before I do that, is M in every single term? What can I do with it then? Cancel it. I'm multiplying every single term by the same number. That means it has basically no effect, or could be 1. Okay, for all it's going to do. If you don't want to cancel it, you can keep it in there and put 70 kilograms into your calculator every time there's an M. For me, that just seems like a chance to make more mistakes. Okay, so before I do anything else, I am going to get rid of all of the M's because they are in every term, and that means it's not necessary. Okay. I just want to get HF by itself. What do I do with G? Divide it over to the other side. Okay, looks like I've got my formula figured out. What did I have to do? Subtract one number and divide one number. It looks like I did a lot more than that though, doesn't it? Looks like I did a lot of heavy algebra lifting there. But in the end, I subtracted one form of energy and then I divided by G. That was it. Okay? All right, so now I can get to plugging in the numbers. So 9.81 times the initial height, which was 30, plus 1/2 times the initial speed, which was 1.5 squared, minus 1/2 times the final speed, which was 7.5 squared, all over 9.81. Okay, that will give me H final. Now, when you punch this into your calculator, I would suggest doing it one piece at a time. Okay, less chance of making a calculation error that way. Okay, so if it were me, this is how I would punch it in. I'd just go 9.81 times 30 and I'd hit enter. Okay, there's my first one. I'm going to add that to 0.5 times 1.5 squared and just hit enter again. Then I'm going to subtract 0.5 times 7.5 squared. And then I'm going to divide that by 9.81. Okay. Did they go very far down the hill? 3 meters vertically. Okay, so they're about 10 feet lower than they were before. Okay? They sped up a lot, went from 1.5 to 7.5 meters per second. Okay, so our final height is 27.2 meters. Okay, it probably seems like a lot the first time you see one of the big ones done. And that's okay. The first time it is a lot. Okay, but in the end, remember this. While it looks like we did a lot of algebra, we really didn't move that many things. Okay? All we really moved was the final kinetic energy over to this side by subtracting, and then we divided G. That was it. Okay? It looks like a lot, but it really isn't. Okay? And once you do a few of these, they're just like the work energy theorem questions. They're patterned. Once you learn the pattern, all you have to do is follow the pattern. okay? And you'll be able to get them right every time. Okay, if you don't have that copied down, make sure you have it copied down. If you have it copied down, then you can take a 5-minute break in the classroom here, walk around, talk, then we're gonna do another one. Okay, write this one down, I'm gonna have you guys try this one. Okay, so we're gonna have a classic roller coaster. Okay, roller coaster is gonna start up here, okay, at the top of this hill, and we'll say that it starts from rest. Okay, and that this hill is 36 meters tall. I want you to calculate for me how fast the roller coaster is going here when it is 7 meters above the ground. We can assume that energy is conserved. There's no friction or anything like that. Okay, I will also tell you that the mass of the roller coaster is 1,400 kilograms. Okay, so similar to the toboggan question, okay, that we just did, except this one's looking for a speed, not a height. Still very similar method. So if you get stuck, you can kind of look back on that last method and see if you can figure out where to go. I'll give you a few minutes and I'll do a little bit more. Okay, give you a few more minutes. Try it in case you get stuck. Okay, so just in case anybody's stuck. Okay, we do want to start this out with the law of conservation of energy. Okay, EI equals EF. Right, obviously that means initial potential plus initial kinetic equals final potential plus final kinetic. Are any of those zero? Which one? Initial kinetic, because our initial speed is 0. Okay, so this I can take out, right? And what I'm looking for, VF, is part of this. So how do I get EK final by itself before I put in any formulas? What do I need to do with EP final? Subtract it over to the other side. Okay? All right, so what I'm going to have, and this is where I'm going to stop, the initial potential minus the final potential equals the final kinetic. Your next step, put the formulas in, manipulate again. Okay? Give you a few more minutes. So after this step here, now we want to put our formulas in. So M times G times H initial minus M times G times H final equals 1/2 M V final squared. Okay, what can I do with the M's? Cancel them. They're in every term. So let's get rid of them so we have less things to worry about. All right, I want to get VF by itself. What do I have to do with that 1/2? Divide it over to the other side. Right now I'm going 1/2 times VF squared. So, all right, so now that's over there. That solves for VF squared. What do I want? Just regular VF. So what do I have to do? Square root. Okay, so if I'm punching in my numbers here, that's going to be the square root of 9.81 times my initial height, 36, minus 9.81 times the final height of 7, divided by 1/2. All square rooted will give me VF. So okay, so roller coaster will be moving at 23.85 meters per second. Okay. Questions on that one? be one where all four have a value. Okay? Okay. Another toboggan question. It's very similar to the other toboggan question that we did. Okay. So at one point, it's 30 meters above the bottom, moving at 14 meters per second. Shortly thereafter, it's moving at 23 meters per second. How far above the bottom is it now? Okay. Start it out. Maybe a picture or some givens. Okay. Then the I equals EF. Go from there. And you can refer back to any of the examples we've done, especially the other toboggan one, and that will help you. All right, so just like the last toboggan question, okay, we're starting up here, and we know that we are 30 meters above ground level, and we're moving at 14 meters per second. Okay, a little while later, we're here. Okay, we don't know what the final height is, but we know that we are moving at 23 meters per second. Okay, and I didn't even bother giving you the mass because what always happens to mass? It cancels, so you don't need it. Okay, I actually had this happen on a test once where I forgot to put the mass on, and a kid came up and asked me what the mass was. I'm like, oh shoot, I forgot to put that on there. And I told him like a number, like 500 kilograms. And then another kid came up a few minutes later, and I couldn't remember what mass I'd given the first kid, and I gave him a different number, and everyone in the class started freaking out. And then I had to remind them that mass doesn't matter. Mass doesn't matter. Okay? All right. We can assume this. Okay? Energy is conserved. It is a law, after all. Okay? And that's going to mean the initial potential plus the initial kinetic equals the final potential plus the final kinetic. Okay? None of those are zero in this question. We have all four forms of energy. What I'm looking for is H final, and that's part of this. So I want to get that by itself right now by subtracting the final kinetic over to the other side. So I'll have initial potential plus initial kinetic minus final kinetic. And that's going to leave me with final potential. Now I can put in my formulas. Okay, m times g times h initial. Okay, plus 1/2 mv initial squared minus 1/2 mv final squared equals m times g times h final. Okay, at this point, we can eliminate all of the masses. And I just need to isolate HF. So what do I do with G? Divide it over to the other side. Okay, so again, it looks like a lot, but we really haven't moved very much. Okay, now I can plug in my numbers here. So 9.81 is G times the initial height, 30 meters, plus 1/2 times the initial speed, 14, squared, minus 1/2 times the final speed, 23, squared, divided by 9.81. Okay, when I punch all of that in, okay, we'll have 9.81 times 30, okay, plus 0.5 times 14 squared, plus minus 0.5 times 23 squared, and then divide that by 9.81. Okay, so we should get 13.03 meters per second. Okay, whoa, stop packing up. Tomorrow, we're going to start off class by going over your need for speed ladders. Okay, and then I'm going to give you some of these problems here to practice with. When we come back from Christmas, it's going to be like review, talk about efficiency, and write a unit exam. Okay, so this is something we have to be good at fairly quickly, which we should be able to because it's nothing we really haven't done before. It's just algebra. Okay? All right.